In this video, I will go into more detail on the ray-sphere intersection. The first slide here depicts a line. So the 3D line is defined as all points P equal to the origin of the line plus the direction times the value t. So O is the origin of the line, and that is a 3D point with coordinates OX, OY, OZ. D is the direction of the line. This is a 3D vector, and the vector is equal to dx, dy, dz. And then t is a singular value which has any value between minus infinity to plus infinity. So using the O plus dt, we can obtain all points along that line. Here we see a 3D sphere. So the sphere is defined according to its center, CS, and CS is equal to cx, cy, cz. We also have the radius of the sphere, which is r. And then we're going to define the 3D sphere algebraically as all points P on the surface of the sphere, such that P minus the center, if we take the square of that, it will be equal to the radius squared. We now have the two equations for the sphere and the line. And what we're going to do is use those two equations to work out the point of intersection between the ray and the sphere. So we want to find the point P, as we can see here, which will be the intersection of the line with the surface of the sphere. So remember, all the points on the line are equal to P, where P equals O plus dt, and all points on the sphere are P, where P minus C squared, CS squared, is equal to R squared. So the first step is to take the line equation, P equals O plus dt, and substitute that into the sphere equation. So we're going to replace the P in the sphere equation with O plus dt from the line equation. So this gives us O plus dt minus C squared. If we take the square of that, it equals the radius squared of the sphere. So remember, here we've got O, which is the origin of the line, that is a 3D point. CS is the center of the sphere, that's also a 3D point. D is the direction, which is a vector, and T is the unknown that we're trying to solve for. We're trying to find the value of T where the line intersects the sphere. So what I'm going to do now is set a new vector V to be equal to O minus CS. So V is a vector from the center of the sphere to the origin of the line. We're now going to take the equation O plus dt minus CS, all of that squared equals R squared, and we're going to replace the O minus CS with the V. So at the bottom of the slide we have V plus dt squared is equal to R squared. We're now going to expand that out, so we get v squared plus 2v dt plus d squared t squared equals r squared. If you have a problem getting from the first equation to the second one there, then you should search for algebraic manipulation, and you can study how to do that. Now I'm going to rearrange that equation to gather the t terms together, so we get d squared t squared plus 2v dt plus v squared minus r squared equals 0. So we have now got an equation in the form at squared plus bt plus c equals 0. And if you're stuck at this point, then search for quadratic formula, and you should be able to see how that's working out. So in that equation, if we match that back to the one that we have, a is equal to d squared, b is equal to 2vd, and c is equal to v squared minus r squared. So let's look at the a first of all. So remember, d is a 3D vector, it's the direction of the line. Therefore, a equals d squared will be calculated as a is equal to the direction vector dot product itself. So d dot product d. The dot product of two vectors is evaluated as the sum of each of their components multiplied together. So if we evaluate that for A is equal to dx times dx plus dy times dy plus dz times dz. So the result of that will be a scalar. And again, if you're having problems here, then search for dot product and you can see how that's being worked out. Similarly, we can calculate B. So B is 2vd. V is the vector between the origin of the sphere and the origin of the line, and d is the direction of the line. And also C, so C is v squared minus r squared. V squared is v dot product itself, and the r squared is the radius of the sphere. So at this stage, we now know each of A, B, and C in the formula AT squared plus BT plus C, where T is unknown. And we can solve for T. So T is equal to minus B plus or minus the square root of B squared minus 4AC over 2A. B squared minus 4AC is known as the discriminant. And we know that if it is negative, then T has no solutions. And this corresponds to the case where ray misses the sphere completely. We know that if the discriminant is positive, then we have two solutions for T, and these are the entry and exit points of the ray on the sphere. And we should take the closest point to the viewer, and this will correspond to the smallest positive T. If the discriminant is 0, then there is just one solution to this equation, and this corresponds to the case where the ray hits the sphere at a tangent to the sphere, so it hits it at a single point.